Good day. This is a Newton's second law question. It's a system. Um, let's look at the question. It says a crate P of mass of 1.25 kg is connected to another crate Q of mass of 2 kg by a light inextensible string. Two crates are placed on a rough, that means there's a friction, rough surface, a constant force of magnitude of 75. If you look at the force that is applied on 2 kg, it's 75 Newton, acting at an angle to the horizontal. Remember, this is pulled at an angle. This force is pulled at an angle. Is applied on crate Q shown in the diagram below. They say the crate accelerates at 0.1 meter per second squared to the right. So we'll choose right as positive. Right, guys, another thing that is important here, there's a tension between the two strings. They exerting a force on each other through a rope. So the tension between them, P is experiencing a tension force to the right. It's a tension force of Q on P. And also Q is experiencing a tension force that is going to the left. It's a tension force of P on Q. And those two tension forces are the same but in opposite direction. They're equal of magnitude but in opposite direction. That's Newton's third law. And another thing here that you need to note here, in this system, they accelerate in the same acceleration. The acceleration of crate P is 0.1 meter per second square, and the acceleration of Q is the same, 0.1 meter per second square. Another thing that you need to notice here, at point P, let's look at the forces that are acting there. Let me use another color. There's a normal force and there's a gravitational force, which are equivalent in that case. And also, since it's accelerating in that direction and we are told it is a rough surface, there's a friction, there's a kinetic frictional force that is going in that direction because it's moving. And let's look at charge. Sorry, let's look at the object Q. There's a normal force and there's a gravitational force there. The normal force and the gravitational force are not equivalent when there's a force that is pulled at an angle, right? I'll dwell on that. And there's a tension force and there's a frictional force that is going in that direction. Their friction are not the same, guys, because they have different masses. And yeah, there are components of that force applied that is at an angle. Since it's pulled at an angle, you have a horizontal component, which is, we call it its fx. It's going to go to the right, and we're going to have a vertical component. It's going to go upwards. Those are the components of that when we resolve that. Now, another thing that is important, let's read the statement below. I'm going to erase that, guys. It's blocking our view there. It says crate P experiences a constant frictional force of 1.8. Crate P, it has a frictional force Fk of 1.8 Newton. And crate Q experiences a constant frictional force of 2.2. So the frictional force here that is experienced by crate Q, it's 2.2 newtons. Right? Guys, let's cut the chase now and go to the question. 2.1. It says state Newton's second law. This is an application of Newton's second law because this object is accelerating. Remember, Newton's second law, it deals with objects that are accelerating. Objects that has an acceleration. It can be decelerating or accelerating. Right? Now, Newton's second law, it says when a net force or a resultant force acts on an object would accelerate in the direction of the motion, and the acceleration is directly proportional to the F net, and the acceleration is inversely proportional to the mass. Right? Stick to the exam guideline when it comes to that, guys. 2.2, it says draw a free body diagram. A free body diagram of crate P. If you're looking at crate P, we've already done the force diagram. So we're going to draw the free body diagram there. So we're going to represent the crate P by a dot. And remember, in the free body diagram, all the arrows needs to be away. You can never draw a free body diagram with arrows that are going towards like this. You will never have a free body diagram like that. You're going to be wrong. So we have a normal force there. And the gravitational force. We have a tension. Tension must be bigger than the opposing force. We have a what? A frictional force. Alright? Because I'm going to draw them both. even though they're not required both, it's just for you to get the feeling of how to draw the free body diagram for both normal force and the gravitational force. We have guys, I'll always advise in the object that has the component of the forces, use the components instead of the actual force. Instead of using the force applied, you can use the components of the force applied. So we'll have Fx and the Fy and the tension force and Fk. This is a free body diagram of object Q. This is for P, which was asking the question. Right, 2.2, it says 2.3, sorry, calculate 3.1, calculate the tension of the string. Right, guys, we are given an acceleration, we're given the masses of the object, we have frictional force. So it's not going to be a simultaneous equation. We're not going to use a simultaneous equation to solve that. They're looking for a tension. So we'll use the second law definition, which is the second law equation. We'll say F net is equal to MA. Guys, in crate Q, it will be difficult for us to find the tension there because we also have another unknown, which is the angle there, the theta. So it will be easy to do it there. In fact, it's impossible to do it here. It's possible to do it in crate P. Let's use crate P. So in crate P, we're going to look at the net forces that are acting on crate P horizontally. Here, there. Right? And remember, we chose the direction right as positive. So our tension there will be positive because it's going to the right, and the friction, it's negative because it's going to the left. It's equal to MA. The tension is the one that we're looking for. The friction we're given at crate P, it's 1.8. And the mass there, it's 1.25. And we multiply by the acceleration, it's 0.1. Now, when it comes to this, it's the math, guys. You have to apply your math. So we'll say T is equal to 1.25 multiplied by 0.1. It's going to be 0.125. And when you transpose that to that side, it's going to be plus 1.8. So 1.25 plus 1.8 is equal to the tension. It's going to be 1.93 newtons. We're done with that question. Let's go to 2.3.2. 2.3.2, it says calculate the angle theta. Remember, guys, we are not given the angle theta there. So it's 3 marks. It doesn't seem long, or we're going to use the simultaneous equation. Now, what are we going to do there when we want that angle? How about we use the mass Q, the crate Q, and says F net is equal to MA. And then what are the forces that are acting there in crate Q here, there, in the free body diagram? Remember the free body diagram, guys, it's a guidance for us in our calculation. So we're going to have negative T, which we have the tension force. And what is the other force that is acting there? It's the friction force, which is negative. It's going to the left, plus the horizontal component is equal to MA. Now, let's substitute now. The tension force, it's 1.93, and minus the FK. We were given the FK there. The FK for the crate Q, we were told it's 2.2. So it's going to be 2.2 plus, and remember the Fx, it's going to be F cos theta. So our F there, it's going to be 7.5. 7.5 cos theta, our unknown, is equal to what is our mass there? It's 2 kg. 2 kg times 0.1. Guys, there again, it's the math. I'm going to just punch the entire thing in the calculator, this. So it's going to be negative 1.93 minus 2.2. It's negative 4.13 plus 7 cos theta. 2 times 0.1, it's 0.2, and then I transpose that, it's going to be 7.5 cos theta is equal to 0.2 plus 4.13. I hope you get that. So 0.2 plus 4.13, it's 4.33. 7.5 cos theta, and then we know we divide by 7.5 both sides. Divide by 7.5. Then our cos theta, it's going to be 0.5773. We're not done yet. And then the answer will do the second function. We'll say theta is equal to cos arc cos is equal to 0.5773. The answer there, it will be, we'll say in the calculator, shift 0.5773. It's the theta there, it's 54.74 degrees. That's it, guys. I hope you understand. Thanks. Bye.